Hello everyone, I'm Nitin from Easy. Topic is the current steering digital to analog converter. Introduction. Digital to analog converters find applications in many systems including communication transmitters and consumer electronics. Among various digital to analog converters realizations, the current steering topology offers the highest speed and becomes de facto solution in gigahertz frequencies, especially if the analog output must be delivered to a resistive load. Current steering digital to analog converters are a more common integrated digital analog compared to digital to analog converters. They are probably the most common biased digital to analog converter architecture. Due to their small size and simplicity, the current steering digital to analog replaces the resistor elements in the register digital analog architectures with the MOSFET current elements and uses some form of summation of the current elements to produce the result. Sometimes the result needs to be a current such as in integrated bias circuits. This current is then passed to the next stage of current mirror bias or passes through a MOSFET stack to produce a set of current mirror bias voltages. Voltage mode digital to analog converters converts the current to voltage with simple resistors or a low output resistance. Transimpedance circuit for improved linearity as shown in figure 3.4. Current source digital to analog converters are attractive due to the lower space used by the MOSFET current elements and the ability to perform some calibration tricks. The resistor digital to analog converter architecture discussed in section 3.1 can be directly repeated using current sources instead of resistors. This even includes the R2R ladder digital to analog converters. Basic topology. We wish to convert an n-bit digital signal D into an analog current IOUT. This can be accomplished as illustrated in figure 1, where each input bit controls a current that is binarily weighted with respect to unit value U. Here D1 denotes the least significant bit, LSB, and DN the most significant bit, MSB. The current sources are scaled up by a factor of 2 from one bit to another to next yielding. The circuit is an example of a simple binary weighted digital analog converter. We can also call it a current switching but not a current steering implementation. An important advantage of this DAC over other types is its ability to drive resistor loads with no need of a buffer. This property proves crucial if the DAC must drive a transmission line as in wireline systems or if the load contains a resistive component as it displays the optical modulators. The current switching structure shown in figure 1 suffers from dynamic errors as depicted in figure 1. When a switch turns off, the top terminal voltage of its corresponding current source collapses to zero. Thus, the next time that this branch is enabled, the capacitance at this terminal must charge up, drawing a significant transient current from the output node. Moreover, since switching actions change the current carried by the array, the ground voltage experience large fluctuations in the presence of parasitic series inductance, such as those due to bond wires. Both of these effects can be greatly suppressed through the use of current steering. Here, the tail current is steered to the left or the right by differential pair causing only a small voltage exertion at node X. Also, since the total array current is relatively constant, the ground boundary is much smaller. Of course, another advantages of this configuration is that it naturally provides differential output. For proper matching among the current sources, we design a unit cell comprising a current source and a differential pair and repeat this cell to form larger cells. That is, cell number J consists of 2 to the power of J minus 1 unit cells in parallel, and the entire digital analog converter contains 2 to the power of n minus 1 unit cells. One drawback of current steering digital analog converters is their limited output voltage compliance. In figure 2, for example, the differential pair transistors must operate in saturation and therefore at least two drain sources voltages are subtracted from the supply VDD. Another difficulty in the design is the choice of the digital input voltage exertions. The most convenient are rail-to-rail swings, but as shown in figure 3, such a choice limit the analog output voltage range Vmax to one transistor threshold if M1 must remain in saturation and leads to large dips in Vx during the transitions of DJ and DJ bar. In other words, we could prefer only a moderate string for a digital inputs with a maximum level less than VTT so as to allow a greater Vmax such swings call for another differential pair and then substantial power consumption. The need for segmentation. The binary weighted array in figure 1 or figure 2 can face undesirable jumps in their output when the digital input goes from 011 to 1000. We observe that the output current is provided by the IU to IU and to the power of n minus 2 IU current sources for the former code and by the to the power of n minus 1 IU current source for the latter. The difference is nominally equal to 1 LSB to IU, but with mismatches present in the circuit, it is possible that the sum of the former groups is substantially different from 2 to the power of n minus 1 IU minus IU. As a result, the DAC input-output characteristics can exhibit a large error or monotonically adjust transition. The fundamental difficulty here is that at this major carry transition, a group of current sources turns off and new current source turns on. The foregoing issue can be avoided by segmentation for n-bit tag. We still incorporate 2 to the power of n minus 1 unit cells but apply a different switching sequence. As shown in figure 5, for a binary input, one cell is activated for 2 and for 00 to 113, etc. We say the cells are driven by thermometer code. For example, as the binary input goes from 01 to 10 to 11, the corresponding thermometer code changes from 0001 to 0011 to 0311. The segmented architecture avoids the jumps shown in figure 4 because at the major carry transition it simply turns on one to more LSB cells rather than turn off one group of current sources. Thus, the output changes monotonically and the jumps is not much different from one LSB as the new cell has come matching with respect to the previous cells. In practice of source, each cell is based on a current steering structure. Partial segmentation. We have seen that the number of unit cells in the is the same for binary and segmented architectures and becomes prohibitively large at high resolutions. For example, 10-bit digital analog converter could require 1023 cells, facing reserve and area and routing issues. We note, however, that the matching requirements are more relaxed for the LSB current sources. Even if the first and second LSB currents have a mismatch of 10%, the overall characteristics can still reach 10-bit precision. Let us consider the following approach. Rather than copy currents by means of unit cell, we seek a method of dividing current by binary factors. For example, we can help doubling the length of the current source transistors as shown in figure 6. However, the effective length does not double, creating significant errors. Instead, we place identical transistors in series. The resulting architecture is called a partial segmented DAK to emphasize the only the MSB section is segmented. The exact partitioning of DSA into a segmented and binary sections depends on the matching properties of the transistors. The binary array can still suffer from effects shown in figure 4 in a typical design. We use binaries weighted for a first 3 or 4 LSBs and segmentation for the remaining bits. Thank you.